In the unending blackness that separates the stars, there is a silence so profound it seems to have a weight. For millennia we have stared into that quiet abyss, shouting our questions into the cosmic wind and hearing only the echo of our own longing. We have searched for a reflection of ourselves, a sign that this intricate, improbable dance of life is not a solo performance on a lonely stage. The universe, in its majestic indifference, has offered few replies. But now, just 20 light-years from our Sun, a mere stone's throw in the galactic neighborhood, a whisper has been detected. It is not a signal, not a message, but something far more fundamental. It is the subtle rhythmic pulse of a world in motion, a celestial body orbiting a faint crimson sun. This is the story of Gliese 251c, a super-Earth nestled within its star's habitable zone. It is a tale of immense distance and tantalizing proximity, a narrative of scientific perseverance, and a profound meditation on the possibility that we are at long last about to meet our twin. Our story begins not with the planet, but with its parent star, a quiet and unassuming luminary known as Gliese 251. This is no blazing, brilliant star like our own Sun. Instead, it is a red dwarf, the most common type of star in the Milky Way, yet nearly invisible to our naked eyes. Imagine the cosmos as a great forest. Our Sun is a towering, magnificent sequoia, bright and dominant, but destined for a relatively short, spectacular life. Red dwarfs like Gliese 251 are the humble, sprawling mosses covering the forest floor in their countless trillions. They are cool, dim, and sip their hydrogen fuel with miserly patience. While our Sun will exhaust itself in another 5 billion years, this small, ruddy star will continue its gentle burn for trillions of years, long after the rest of the universe has grown dark and cold. It is a stellar furnace of immense endurance, a beacon of stability in an often violent cosmos. And it is around this paragon of longevity that our subject makes its home. Detecting a world like GJ 251c is an act of supreme scientific artistry. You cannot simply point a telescope and see it. From 20 light-years away, the planet is utterly lost, swallowed by the faint glare of its own sun, a firefly next to a distant bonfire. So astronomers had to learn to see the unseen. They turned to an ingenious method, a technique of cosmic inference that listens for the gravitational dance between a star and its orbiting worlds. This is the radial velocity method, the art of the stellar wobble. To understand it, picture a professional ballroom dancer spinning with perfect balance and grace at the center of a vast, dark stage. Now imagine this dancer is holding a small, unseen partner. As they spin together, the partner's mass, though smaller, pulls on the main dancer, introducing a subtle rhythmic sway. The dancer is no longer spinning around their own perfect center, but around a shared center of gravity. From the far end of the hall, you cannot see the smaller partner, but you can observe the larger dancer's delicate repeating wobble. By measuring the speed and the timing of that oscillation, you could deduce the mass of their invisible companion and how far away they are orbiting. This is precisely how we found GJ 251c. For years, astronomers at the Calar Observatory in Spain used a powerful instrument named Carmen's, a spectrograph of exquisite sensitivity. Its job was to stare night after night at the faint light of Gliese 251. It wasn't looking for an image, but for a shift in the starlight's color. As the star wobbles towards us, pulled by its unseen planet, its light waves are compressed, shifting slightly towards the blue end of the spectrum. As it wobbles away, the light waves are stretched, shifting towards the red. This is the Doppler effect, the same phenomenon that changes the pitch of a passing siren. The effect caused by a small rocky planet is almost immeasurably tiny. It is a change in the star's velocity of just a few meters per second, the pace of a brisk walk. Discerning this signal from the star's own boiling turbulent surface is like trying to hear a single cricket chirping in the middle of a hurricane. It required hundreds of observations spread out over years, piling up data, filtering out the noise, until a clear periodic signature began to emerge from the static. A pattern repeating every 14.2 days. The signature of a new world. When the calculations were complete, the nature of this hidden sphere began to take shape. Its mass was estimated to be at least 4 times that of Earth. This places it firmly in a fascinating class of planets known as super-Earths. These are celestial bodies more massive than our own terrestrial home, but significantly less massive than ice giants like Uranus and Neptune. Curiously, this is the one class of planet our own solar system lacks, yet appears to be one of the most common in the galaxy. We live in a planetary system that is, it seems, the exception, not the rule. A 4-Earth mass world is a place of profound geological possibilities. The gravitational pull on its surface would be substantially stronger. Mountains might not be able to reach the soaring heights of the Himalayas, as their own weight would press them down. Tectonic plates, if they exist, would grind against each other with unimaginable force, perhaps leading to colossal planet-shaking quakes. Any volcanoes would have to work harder to push magma to the surface, potentially resulting in eruptions of a scale and violence that would dwarf anything in Earth's history. A stronger gravity could also have a profound effect on a potential atmosphere, clinging to it with a more tenacious grip, making it less likely to be stripped away by solar winds over eons. This could result in a denser, thicker blanket of air shaping the world's climate in ways we are only just beginning to model. This is not merely a bigger version of Earth. It would be a fundamentally different kind of rocky world governed by a more powerful and relentless gravity. More exciting than its mass, however, is its location. GJ 251c orbits its red dwarf star at a distance that places it smack in the middle of the so-called habitable zone. This is a concept often nicknamed the Goldilocks Zone, and the analogy is remarkably apt. Think of a star as a campfire on a frozen night. If you pitch your tent too close to the flames, you'll be incinerated. If you set up camp too far away, you'll freeze in the unforgiving cold. But there is a temperate, comfortable ring of distance around the fire, not too hot and not too cold, where you can exist in comfort. For a planet, this comfort is defined by one precious substance, liquid water. In this orbital band, the energy from the star is just right to allow water, should it exist on the planet's surface, to remain in its liquid state, forming oceans, lakes, and rivers. Too close, and the water would boil away into space. Too far, and it would be locked into a permanent global sheet of ice. Because Gliese 251 is so much cooler and dimmer than our Sun, its habitable zone is huddled much closer to the star. GJ 251c completes a full orbit its year in just over 14 Earth days, whipping through space at a tremendous speed in its tight, intimate circle. It lives in a perpetual gentle warmth, bathed in the ruddy light of its parent sun. This placement is the first and perhaps most crucial checkmark on the list of ingredients for a life-bearing world. Yet orbiting so close to a red dwarf star presents a unique and exotic set of conditions, a strange reality that would be utterly alien to us. The most dramatic of these is a phenomenon known as tidal locking. Just as the Earth's gravity has locked one face of our moon to permanently face us, the immense gravity of Gliese 251 has likely locked its nearby planet in a similar embrace. This means one hemisphere of GJ 251c is trapped in perpetual daylight, staring unblinkingly at its sun for all eternity. The other hemisphere is cast in an endless frozen night, having never felt the warmth of its star. This is a world cleaved in two. The dayside could be a scorched, sun-blasted desert, where any surface water has long since boiled away. The night side could be a cryo world, a landscape of nitrogen, ice, and frozen gases, one of the coldest places imaginable. Life as we know it could not survive in these extremes. But between these two inhospitable realms there exists a sliver of potential paradise, a twilight zone. This is the Terminator line, a permanent ring of dawn and dusk that encircles the entire planet. Here, the red dwarf sun would hang eternally on the horizon, never rising, never setting. The light would be a constant, gentle crimson, casting long, dramatic shadows across a landscape of perpetual twilight. Temperatures could be mild and stable, allowing liquid water to flow. If great oceans exist on this world, powerful winds driven by the extreme temperature difference between the two hemispheres would whip across the planet, potentially circulating heat and creating a band of stable, habitable climate along this Terminator ring. It is here, in this realm of eternal sunset, that the search for life would most likely begin. This quest for other worlds, for a sibling to Earth, is not a new one. It is a dream woven into the very fabric of human history. 2.5 millennia ago, the Greek philosopher Epicurus, gazing at the same stars we see today, wrote of infinite worlds, some like ours, some unlike. He reasoned that in an infinite universe, it was illogical to assume that this single speck of dust was the only one to harbour life. It was a breathtaking leap of intuition, a thought that would echo through the ages. In the 16th century, the Italian philosopher Giordano Bruno expanded on this, declaring that countless suns existed and that countless earths revolved around them. For this and other heresies against established doctrine, he was burned at the stake, a martyr to the idea of a pluralistic cosmos. Centuries later, as telescopes grew more powerful, our gaze fell upon our planetary neighbours. Percival Lowell, an American astronomer, spent years meticulously mapping what he believed were intricate canals on the surface of Mars, convinced he was seeing the grand engineering projects of a dying civilization. He was wrong. His canals, a tragic illusion born of hope and optical tricks, but his passion ignited the public imagination. The idea of life beyond Earth had moved from philosophy to scientific inquiry. The true revolution, however, arrived in 1995. Swiss astronomers Michel Mayor and Didier Queloz were monitoring a sun-like star called 51 Pegasi. They were using the very same stellar wobble technique that would one day reveal GJ 251c. And they found a signal, a massive planet half the mass of Jupiter, orbiting its star in a blistering 4-day period. This was a hot Jupiter, a type of world that our theories of planet formation said should not, could not, exist so close to its sun. It was the first confirmed exoplanet around a sun-like star, and its bizarre nature shattered our neat and tidy models of the cosmos. It taught us a vital lesson. The universe is more creative and more surprising than we could have ever imagined. In the decades that followed, our pace of discovery accelerated exponentially. Telescopes like Kepler and TESS were launched into space, staring unblinkingly at vast patches of the sky, watching for the telltale dimming of a star as a planet passes or transits in front of it. They unveiled a galactic menagerie of worlds, gas giants, ice worlds, lava, planets, and ocean spheres. The data poured in, and the conclusion was inescapable. Planets are not a rare exception, they are the rule. Nearly every star you see in the night sky is now believed to host a family of planets. Our galaxy is teeming with at least 100 billion worlds. GJ 251c represents the next phase of this grand exploration. We are no longer just counting planets. We are now taking their measure, sifting through the census to find the worlds that are close, that are rocky, and that lie in that all-important temperate zone. We are searching for an address. But what does it truly mean for a world to be habitable? The presence of liquid water is a magnificent start, but it is merely the opening chapter of a much longer, more complex story. A planet must also possess a substantial atmosphere. This gaseous blanket serves multiple critical functions. It provides the necessary surface pressure to keep water from boiling away into space. It acts as a thermal regulator, trapping heat through the greenhouse effect and circulating it around the planet, smoothing out extreme temperatures. And crucially, it shields the surface from harmful radiation. This is especially important for a planet like GJ 251c. Red dwarf stars are known for their violent, unpredictable tempers. They can suddenly erupt in powerful stellar flares, unleashing torrents of high-energy particles and X-rays that would be lethal to any unprotected life on a nearby planet. A thick, robust atmosphere would be the first and most important line of defense. Beneath that atmosphere, another shield is required, a magnetic field. Here on Earth, our global magnetic field is generated by the churning molten iron core deep within our planet. This invisible force field extends far out into space, forming a protective bubble called the magnetosphere. It deflects the constant stream of charged particles from the sun, the solar wind, which would otherwise scour our atmosphere away over millions of years. Without a magnetic field, Earth would eventually look like Mars, a dry, cold world with a whisper-thin atmosphere, its oceans long since vanished. For GJ 251c to be truly habitable for the long haul, it too would need an active geologic heart, a molten core generating a planetary shield to protect its air and water. Finally, there is the slow grinding dance of plate tectonics. On Earth, the crust is broken into massive plates that drift and collide, driving geological processes that are vital for long-term habitability. This process recycles minerals and chemicals, burying carbon in rocks and releasing it through volcanic activity. This acts as a planetary thermostat over geological timescales, regulating the amount of carbon dioxide in the atmosphere and preventing the climate from spiraling into a runaway greenhouse or a permanent deep freeze. It is the planet's own life support system, a complex feedback loop that has kept our own world temperate for billions of years. So when we ask if GJ251c is habitable, we are not just asking about its orbit. We are asking, does it have air? Does it have a magnetic shield? Does its very ground churn and recycle the elements needed for life? These are the profound questions that separate a merely well-placed rock from a living, breathing world. Let us for a moment indulge in a flight of informed imagination. What might it be like to stand on the surface of GJ251c within that promising terminator zone? You look up at the sky. It would not be the familiar blue of Earth. A red dwarf's light is predominantly in the red and infrared parts of the spectrum. The sky might be a perpetual dusky orange or perhaps a deep bruised purple. The star itself would appear much larger in the sky than our sun, a huge crimson orb hanging motionless at the horizon. The light would be dim, perhaps as bright as a heavily overcast afternoon on Earth, but the radiant heat would be palpable. If plant life exists here, it would have evolved to thrive on this different quality of light. Photosynthesis on Earth is optimized for the yellow-white light of our sun, making plants green. Here to absorb as much energy as possible from the dim red light plants might be a deep dark purple or even black covering the landscape in strange otherworldly forests. The winds would be a constant, powerful presence, a relentless flow of air from the hot day side to the cold night side, a global river of wind that would shape the geology and the biology. Creatures, if they exist, might be low-slung and powerfully built to withstand the higher gravity and the persistent gales. If oceans are present, they would be dark and turbulent, their surfaces whipped into a frenzy by the ceaseless winds. This would not be a carbon copy of Earth. It would be a world both familiar and deeply alien, a testament to the endless adaptability of nature. It is a vision that transforms a data point in an astronomical catalogue into a tangible, breathtaking place. The discovery of GJ251c is a monumental achievement, but it is only the beginning of its story. Right now, it is a ghost, a world we know only through its gravitational tug. The next great challenge is to see it, or more accurately, to analyze the light that has passed through its atmosphere. This is the domain of our next generation of super telescopes, most notably the James Webb Space Telescope and the ground-based Extremely Large Telescope. Their prime mission is to characterize the atmospheres of worlds just like this one. For this to work, we need a stroke of geometric luck. The planet's orbit must be aligned perfectly from our point of view, so that it passes directly in front of its star, an event called a transit. If it does for a brief period, the star's light will dim slightly, but more importantly, a tiny fraction of that starlight will filter through the planet's atmosphere on its way to our telescopes. Within that filtered light, a chemical fingerprint of the air is imprinted. Different molecules in the atmosphere absorb specific colors or wavelengths of light. By analyzing the starlight that is missing, we can determine what the atmosphere is made of. We can search for the telltale signatures of water vapor, carbon dioxide, and methane. And we can look for the holy grail of astrobiology biosignatures. These are gases that are unlikely to exist in large quantities without the influence of living organisms. On Earth, the most prominent biosignature is oxygen. Our planet's oxygen-rich atmosphere is a direct product of billions of years of photosynthesis. Finding abundant oxygen in the atmosphere of GJ251c would be a staggering revolutionary discovery. It would be the closest thing to definitive proof of life beyond Earth that humanity has ever encountered. We do not yet know if GJ251c transits its star, but astronomers are watching and waiting, hoping for that lucky alignment that will allow us to take our first breath of alien air. Even as we dream of analyzing its atmosphere, we must confront the sheer mind-numbing scale of the distance that separates us. 20 light years. The number sounds deceptively small, but a single light year is the distance light travels in 1 year, nearly 10 trillion kilometers. 20 light-years is an expanse so vast it defies all human reference. If you were to board our fastest current spacecraft, the Parker Solar Probe, and point it in the direction of GJ 251c, the journey would take over 35,000 years. Civilizations would rise and fall on Earth. The very languages we speak would evolve into unrecognizable forms before that lonely probe arrived at its destination. The distance is the great tyrant of interstellar exploration, but humanity is nothing if not a species of audacious dreamers. Projects like Breakthrough Starshot are already conceptualizing how to bridge these immense voids. The idea is to build fleets of tiny gram-scale nanocraft, each with a solar sail thinner than a human hair. A powerful array of lasers based on Earth would focus a beam of light onto these sails, accelerating them to 20% of the speed of light. At such incredible velocity, the journey to Gliese 251 could be reduced from millennia to a single human lifetime, perhaps a century. The probe would be a fleeting visitor screaming past the planet in a matter of hours, frantically snapping images and collecting data to beam back home on a whisper of a laser beam. It remains the stuff of science fiction for now. The technological hurdles are immense, but it is a plausible roadmap, a sketch of a future where we can reach out and touch these neighboring worlds. So we are left here on our own blue marble, staring across an ocean of vacuum at a potential sibling world. The existence of a place like GJ 251c forces us to confront the most profound questions of our existence. It amplifies the famous Fermi paradox. If the galaxy is filled with potentially habitable worlds, where is everybody? Why is the cosmos so silent? Perhaps life is incredibly rare, the product of a chemical fluke so improbable it has happened only once. Or perhaps civilizations are common, but they inevitably destroy themselves before they can master interstellar travel. Or maybe, just maybe, they are out there, and the silence is simply the mark of a vast, untraversed distance, a quiet that is waiting to be broken. The discovery of a nearby rocky temperate world transforms this from a philosophical game into a tangible scientific pursuit. It provides a specific target, a place to point our instruments, our hopes and our dreams. It reinforces the Copernican principle, the idea born centuries ago that we are not special. Our planet is not the center of the universe. Our sun is an ordinary star, and our galaxy is one of billions. And now we see that worlds like ours may be a common feature of the cosmic landscape. This is not a demotion, but a promotion. It means we are part of something immeasurably vast and wonderful. We are members of a galactic community, even if we have yet to meet our neighbors. GJ 251c remains a world of potential, a realm of tantalizing possibility. It could be a sterile rock baked on one side and frozen on the other. It could be a water world, its surface covered by a global ocean. It could be a living sphere teeming with organisms adapted to its eternal twilight. We do not yet know, but the uncertainty is what makes the journey so compelling. For 20 light-years, the light from its star has traveled unimpeded, crossing the interstellar void to fall upon our telescopes, carrying with it a subtle story of a wobbling star and its hidden companion. It is a reminder that the universe is filled with secrets waiting for a curious species on a distant planet to build the tools and the patience to uncover them. Our nearest twin might be waiting for us just next door across the silent, starry expanse. And our conversation with the cosmos has only just begun.